those two kind of go back and forth. Next, you select a speed controller to match the motor being used. You always want the speed controller to be able to handle the full rated current of the motor. And then finally, you select the right prop to get the desired performance. There may be a couple of different props you can use. Some will make more thrust but less speed, and others will make more speed but less thrust, but they all pull the same power. So that's kind of the fine-tuning of the final system. Now, if there was one slide in this whole presentation that I would say is the most important slide, if I could only show you one slide, it'd be this one. It's what I call the 80% rule. What the 80% rule means is, well, it's basically the most important thing you'll ever learn about electric flying. Never run any component at more than 80% of its maximum rated value. If you do that, you will almost never burn out a battery, motor, or speed controller. Virtually all problems that people have with electrics, they have because they're pushing their system past this 80% rule. You know, it's the guy that's going, yeah, my speed controller's rated for 60 amps, and yeah, it pulls 70 at full throttle, but I don't use full throttle that much. You know, and they don't know that they're pulling at 120% power all the time from their system, and eventually it's going to fail. The motor's rated for 80 amps, for example. Keep it under 64 amps. If ESC is rated for 100 amps, keep the maximum current it feeds, you know, down to 80 amps. If you've got a battery rated for 4,000 milliamp hours, you should only take 3,200 milliamp hours out of that pack. Leave 20% of the energy in the battery, and you'll double or triple the life of the pack. If you pull a battery down 100% power every cycle, you maybe get 50 charge cycles out of the battery. It'll be dead. If you leave 10% in, you can get it to go up to 100. If you leave 20% of it in, you can get it to go up to 300 or 400 charge cycles. So, you know, it's your batteries. You know, if you want them to last long, you know. And the other thing is, never exceed the C rating. If a battery's rated for 25C, never pull more than 20C. If you do this on every one of your power systems, you'll never have any problems with it. Following the 80% rule gives you trouble-free operation. It gives you the maximum life out of your parts. I think the battery's being low on my clicker here. Electric flight does require some special tools. If you don't have the special, you know, the correct tools for electric flying, it's going to cause you a lot of problems. Don't be afraid to spend a little bit of money up front on the proper tools. When you fly glow, you got to have a glow battery, you got to have a starter, you got to have, you know, certain tools and things like that. With electrics, you don't have to have the tools. But if you don't have them, it's going to cause you a lot of grief. If you burn up one motor or speed controller, you're going to spend more money on that than you would if you bought all the tools that you need together. This is what I consider the must-have list of tools when you're flying electrics. The first one is a watt meter. These are also called power meters, power analyzers. Basically, you put this in line between your battery and your speed controller, and it will tell you how many amps of current you're pulling, what your battery voltage is. And in some cases, you can have sensors that can tell you how fast the motor's running and all kinds of other things. Another tool is a voltmeter. Now, it's a crime if you don't have a voltmeter, because you can buy this voltmeter at Harbor Freight for $2.99 on sale, okay? I mean, it's less than a cup of coffee. So, with a voltmeter, you can measure battery voltages, you can test circuitry, you can see if circuits are open or closed. There's all kinds of things you can do with a voltmeter. Next thing is a good soldering iron. In fact, this is the actual soldering iron that I use. It's a Weller WC100 40-watt solder station. It's $39, you know, online or most of those electronic stores. You really need to have about a 40-watt iron for soldering Deeds connectors, bulk connectors, stuff like that. And finally, a really cool little tool that I absolutely love is a pulse meter. This one's made by Electronic Model Systems. What this does is it tells you what the pulse is coming out of your receiver. In a radio system, each channel of your receiver sends little pulses that vary between 1 millisecond and 2 milliseconds to control the servos. On a throttle channel, 1 millisecond is full idle, 2 milliseconds is full throttle. 1.5 milliseconds is 50% throttle. Well, 1.7 milliseconds is 70% throttle, and so on. Same thing with aileron. You know, 2 milliseconds might be full right, 1 millisecond might be full left, and then 1.5 milliseconds in the middle. A lot of times when you're trying to troubleshoot a system and your speed controller don't work, you don't know what's going on, this is so handy because a lot of times in an electric power system, you have a speed controller melt down or something, it can fry the throttle channel in your receiver, and you don't even know it. All the rest of the channels still work, but maybe burnt a trace out of the circuit board. If you've got one of these meters, you can find that out and save you hours of troubleshooting time. A few words about soldering. As I said before, you're going to have to learn how to solder if you're going to get to electric. Proper soldering is the most important skill you can have. One bad solder joint can easily destroy a motor or a speed controller. Another thing is never trust pre-tinned leads on anything. You know how you get your speed controllers and the leads are already, they already got solder on them? All of the products that are manufactured today are required to use what's called ROHS solder. It stands for removal of harmful substances. And basically what it is it's lead-free solder, so it doesn't harm the environment. It melts at a much higher temperature than the standard 6040 or 6337 solder we buy at Radio Shack or someplace like that we make all our solder connections with. If you don't re-tin the leads on your speed controller, what will happen is the solder will melt on the connector, but the solder in the wire won't melt. And you end up with a very cold, brittle solder joint that will crack and break open sometime in the future. And if that happens between the motor and the speed controller and you lose power on one of the phases, the motor instantly locks up, goes to full rotor current, and explodes the speed controller. So you want to make darn sure you got really good solder joints, especially between the speed controller and the motor. Always re-tin the leads and connectors with the actual solder you're going to solder with before you do any soldering, to make sure that you've put some of the lower temperature solder into these parts before you solder it. And another thing is never, ever, ever use acid core plumbing solder. You wouldn't believe the number of speed controllers we get back and the wires are all corroded and green and stuff because some guy used acid core plumbing solder from his plumbing kit. Yeah. You want to always use a rosin core electronic solder.
Can I ask you a question?
Yeah.
I do some plumbing around the house too, so I've used gotten in the habit of using flux, and I found that it makes soldering a lot easier.
You can get solid solder, and you can get a rosin core non-acid flux. Some guys like doing that, and if you have a solder and you have a non-acid flux that's rated for electronics, you can do that. Brush a little flux on both the parts and then melt the solder in there.
Any concern over time the flux left over flux?
No, as long as it's a non-acid solder that's safe for electronics, it's not going to be a problem. Finally, to kind of wrap this all up, I want to take the last 5 minutes of the presentation and kind of walk you step by step through the process of selecting a power system so you all know how to do it. And this whole process is on the back side of this handout I'm going to give you too, so you'll have that as well. For this example, I'm going to use a 45 size ugly stick airplane that weighs about 6 pounds, ready to fly. And I wanted to have like pattern ship, really good performance. Step one is to calculate how many watts of power is needed. I can do this a couple of different ways. Using the 2,000 watts per cubic inch method, if you take 2,000 times 0.45, I get 900 watts of power that I'm going to need for this plane. Using the 150 watts per pound method, because it's a pattern ship, and earlier you might remember I said you wanted about 150 watts per pound. If you take 150 watts per pound times 6 pounds, you also get 900 watts. So in this case, using either method gives us the same result. So it looks like we're going to use 900 watts of power for this model. Step two is selecting the proper size battery. The battery capacity is determined by how much current is needed and how long we want to fly. We're going to start by determining how many cells we're going to use. Now, a 4-cell pack from that chart earlier was good for 450 to 1100 watts, and a 5-cell pack is good for 700 to 1700. Well, 900 is kind of getting up at the top end of the 4-cell pack, and the higher the cell count, the more efficient the power system is. So in this example, I'm going to go ahead and use a 5-cell pack because that's going to give me the ability later on down the road, if I want a little bit more power, I'm going to have a battery that's going to be capable of delivering. And since higher voltage equals better efficiency, I'm going to go with 5 cells in this example. So we're going to check, remember that 2 to 5 range I talked about, power to, or voltage to current. If we take 900 watts and divide it by 18.5 volts, which is what a 5-cell pack puts out, we're going to have to pull about a little over 48 amps of current. Now, if I take 48 amps divided by 18.5 volts, my ratio is 2.6. So I'm right in the middle of that 2 to 5 range, actually towards the lower end, which is going to give me better flight times. Next, we're going to determine the battery capacity. This thing's going to pull, like I said, about 48 amps at full throttle. But if I go back to 2/3 throttle, I'm only going to pull about 24 amps of current. And so, because in my ugly stick plane, it's not a pylon racer, I'm not going to be flying at full throttle the whole time. Most of the time I'm going to be back around 2/3 throttle. I'm going to use that current value to set the battery pack. The current value you use to determine the battery depends on the kind of model that you're going to fly. You know, for example, if it's a pylon racer where you're flying at full throttle the whole flight, then obviously you need to use the full throttle current rating. For a sport type model, you know, that's going to be flying around 2/3 throttle most of the time, you can use half of the full throttle current. And for a trainer type airplane, where you're flying around at half throttle, you're only going to be pulling about 1/3 the full throttle current at half throttle. So you would use that value for a trainer. Now, since this is a sport type model, we're going to use half the current and use 24 amps in this battery example. So now we're going to determine how long we want to fly. Well, most of you guys that fly, you know, globe, like to be able to have a 10-minute flight, so we're going to use 10 minutes of flight time. A 1C discharge is 60 minutes, remember, so for 10 minutes, that's going to be equal to a 6C discharge rate. And if we need 24 amps of current, and at a 6C rate to determine the battery capacity, we take the amperage divided by the C rate, and we get a 4 amp hour battery. That's how long a 4 amp hour battery running at 24 amps will last for 10 minutes. Now, a 4 amp hour battery is also a 4,000 milliamp battery. So now we know we need a 5-cell 4,000 milliamp battery, right? Pretty straightforward. Except for one thing. Oh, we don't want to forget that 80% rule. Remember, we only want to take 80% of the energy out of each battery and leave 20% in it. So what we're going to do is we're going to bump that pack up. If we did use the 80% rule and we stuck with a 4,000 pack, we'd only want to fly 8 minutes instead of 10. If we want to get that full 10 minutes, then you just step up from a 4,000 pack to a 5,000 pack, and you're going to be able to get that full 10 minutes of flying time and have 20% reserve left at the end of the flight. So now we've got our battery selected. We need 900 watts of power, and we're going to use a 5-cell pack, either a 4,000 or a 5,000, and we're going to set our flight time to either 8 or 10 minutes, depending on which size battery pack we choose. The next step is selecting the motor. Now, you need to look for a motor that's going to deliver 900 watts of power from a 5-cell pack, and which means it's going to pull about 48 amps. If we use the 80% rule and we actually need 900 watts of power, we're not going to look for a 900 watt motor. We're going to look for an 1125 watt motor, something a little over 1100, so that when we run at 900, we're only running it at 80% power. Another consideration in this specific example is prop size, because as you know, 45 size ugly stick's a tricycle geared airplane. You know, and you only got about that much clearance from the spinner to the ground, so we got to limit ourselves to no more than an 11 or 12 inch prop. In this example, the prop's going to be hitting the runway. So not only do we have to maintain our wattage, but we also got to do it with either an 11 or 12 inch prop. Now, this is where prop charts come in very handy. Without them, it's pretty much of a guessing game. And this is the one point in the presentation where I put a shameless plug in for my company. We're the only company out there that actually creates full prop charts for our motors. And we do this to make selecting a motor easy for you guys, so you don't pick the wrong motor and burn it up. Because it doesn't do us any good if we sell you a motor if you're not happy with it. Come on. There we go. At Innovative Designs, we take a lot, and I mean a lot of time to do these prop charts. Every one of those motors on that board took almost an entire day's worth of work to create the prop chart. And that's not the whole product line. So I've probably got 4 solid months of just generating prop charts on these motors. Without a prop chart, you have to look at the manufacturer's ratings, and a lot of times, good luck on that. So I'm going to take a look at a prop chart. I looked through a bunch of prop charts, and the motor that I came up with in this example that fits all the criteria is a Cobra 3520-10 motor from our website. This is the prop chart for that motor. Now, remember what we're looking for. We're looking for a motor that's around 1125 watts, maximum power. Look at this one, 1150, perfect. We're also looking for a motor that can handle about 48 amps of current on 5 cells. Well, this is the 5-cell section of the chart. And so we kind of look down here, we're looking for 48 amps, and oh, look at this, from 11.7 at 18.5 volts, 48.8 amps, 903 watts. We were looking for 900. So we got our 1125 maximum watts here. This prop is going to make us 900 watts, and it's an 11.7. It falls into our 11 or 12-inch criteria. Another prop we could use was maybe a 12.6, a little bit more current, 54 amps, 1,000 watts of power. But, the one that just nails it is this 11x7. It meets all our specifications perfectly. So that's the prop I'm going to use, is that 11x7. Finally, we're going to select the speed controller. And again, we want to use that same 80% rule. Well, we're using, from the chart back there, the maximum current rating of this motor is 62 amps. And we're pulling 48 amps from with an 11x7 prop. If we take 48 amps divided by 0.8, we get 60 amps. And the 60 amps is pretty darn close to the 62 amps maximum current rating for that motor. So a 60 amp ESC would be ideal in this situation. Now, if you wanted to, Cobra makes a 60 amp 6-cell speed controller, so bang, that's the one we want to use. But if you want to step up to an 80 amp, it's only 10 bucks more. And it's not going to hurt anything. It's just going to run cooler. And then later on down the road, if we do want to run that 12.6 prop and we're pulling 54 amps, then we're still meeting the 80% rule for this 80 amp speed controller, because that's good for up to 64 amps. So then this is where sometimes, it's cheap insurance. You got a $500 airplane and you're going to spend 10 more bucks, to make your speed controller run a lot cooler. And then finally, this is that prop chart again, selecting the prop. You see, 48 amps, we could use this 11.7. We could also use a 12.6. But you see down here, we also got a 13.4 that pulls 46 amps. If we were doing something like a Piper Cub that we only wanted to fly at maybe 40 miles an hour, this 13x4 prop pulls a plane at 42 miles an hour. So we might want to use that, if it was a Piper Cub instead of an ugly stick. But that's where that prop chart comes in really handy. So wrapping it all up. Hopefully, I haven't run through this so fast and made your brain hurt. Electric power systems do require a new set of skills to be learned, and it does take a little bit of work to put it all together. But in the end, the benefits do outweigh the extra time and effort that it takes to learn, the new skills and to set up a good power system. Hopefully, you've all learned something here tonight and enjoyed the presentation. Thanks for listening. We're Innovative Designs, and we're the distributor of Scorpion motors, Cobra motors, and Next Level multi-rotors. And that concludes the presentation. So if you guys have any questions, I'd be happy to answer them for you. Yeah?
On your magnetic field, what is the most efficient magnetic field created by more lines of finer wire or heavier lines of heavier wire and fewer lines?
It completely depends on the motor. In most cases,
Weight-wise, which is the lightest power source?
In most cases, you're going to get higher efficiency out of fewer turns of bigger. Well, there's two ways you can interpret the question. You can wind a motor with multiple strands of a smaller wire to get the effect of a bigger wire to make it easier to wind. The single bigger wire is going to be more efficient because the wires are coated with an enamel insulation, and that takes up some of the space of the wire. And the thickness of that insulation doesn't change much with the size of the wire. So if you're winding it with a lot of little strands, you're going to have more insulation and less copper. So it's going to be a little less efficient. Now, if you've got a couple of different motors, and one's got a lot of turns versus less turns, so that changes the kV of the motor. So when you have higher numbers of turns of smaller wire, and you run that motor at a higher voltage setting because it has a lower kV, then that setup's going to be more efficient than fewer turns of big wire running at a lower voltage because you're going to be pulling more current. The losses in an electric motor are based on the current. any of you guys ever heard of what's called I squared R losses in electrical systems? You may or may not. I stands for current. And as you change the current in a power system, the amount of energy you lose goes up as a function of the square of the current. So if you have a system pulling 20 amps and a system pulling 40 amps, there's going to be not twice as much loss, but 4 times as much loss in the system pulling 40 amps as there is in the system pulling 20 amps. So if you have a 20 amp system at 10 volts versus a 20 amp system versus a 40 amp system at the lower voltage, the higher voltage system is always going to be more efficient.
And that's why it's basically heat.
Yeah, and that loss creates heat in the core of the motor and makes the motor hot.
Okay, the basic question is, for the weight of the motor, let's say you're producing 1 horsepower. To produce 1 horsepower, which is the lightest motor, either the fine wire with the windings or the heavy wire?
You need a motor that's going to make 746 watts of power to make a horsepower.
Right. Which one's going to be lighter?
Well, a 746 watt motor is a 746 watt motor.
Like a
They're the same weight. You can
Which one's lighter, the one wound with fine wire or the one wound with heavy wire?
Well, they're both going to be the same weight. If you got 20 turns of small wire versus 10 turns of big wire, you're going to put the same amount of copper in the motor, so they're going to weigh the same.
Yeah, but you can pump more current through the heavier wire, creating more magnetic field.
But you have to do it at a lower voltage because when you put less turns on the motor, the kV goes up.
So what's the answer?
I've told you 3 times already, they're both the same.
It's the same answer.
You can't put more turns on a motor and not change the characteristics of the motor.
You're going to wind your own motor.
If you put fewer turns of bigger wire on a motor, it's going to spin faster. And so you're either going to have to run on less voltage to use the same prop, or you're going to have to run a smaller prop at a higher RPM at the same voltage. And in that case, the system's going to be much less efficient. So the most efficient motor is going to be smaller wire, more turns on a higher voltage, and both motors are going to weigh the same because they're both the same wattage.
Because the rule of thumb, the 3 watts per gram.
The 3 watts per gram rule of thumb comes from motors that are about 80% efficient.
So you're at
Yeah, like a Scorpion motor can be 85 or 90% efficient, so some of them can handle as much as 5 watts per gram.
Quick question.
Mm-hmm.
In a lot of electronics applications, we use twisted pair wires
Mhm.
to cut down on
To
electronic noise.
reduce noise, yeah.
In a lot of electric power setups that I've seen, no one uses twisted pair
Mhm.
for the power wires, and I was wondering why that is.
Well, you talking on the input or the output side?
Both.
You don't want to do it on the output side because if you wrap the motor leads around each other, remember, two wires are feeding power back and forth and one's carrying signal. So if you wrap the wires around each other, you can get like junk signals going down the signal line and cause the motor to fire at the wrong time. And when you get that effect like you're throwing stones into the propeller while the engine's running. And that is like horribly hard on both the motor and the speed controller. When you do that, it can rip the magnets out of the motor and it can blow the transistors out of the speed controller when that happens.
What about the leads from the ESC?
From the battery to the ESC, you can twist them because that's DC current. There is a small AC component in it because every time the transistors fire, you get a rush of current that comes in and out, back and forth. It's not really steady state. It's like a lot of pulses. So twisting the input leads will reduce radio noise a little bit, but it's such a low frequency that it's so far away from anything in the radio spectrum that you're doing it really doesn't have any effect on it.
And that would be at that 8 kilohertz frequency?
Yeah, that would be around the 8 kilohertz frequency.
Thank you.
How crucial is to put additional capacitors on the heat pump between battery and speed controller?
If you're running long motor leads, longer than about 8 inches, because usually you got about 4 inches of wire on the battery and about 4 inches of wire on the speed controller. What happens is when you got, leads this long, like some of my big pusher jets, I got the battery way in the nose and the motor in the tail. The every time you fire one of those transistors, you have a momentary short circuit when it switches to the next phase. And so you can get a lot of what they call ripple because the voltage will pull down every time the transistors fire because you've got a lot of resistance of wire. So you should, if you're going to go more than about 2 feet of wire, you should add an extra set of capacitors onto the speed controller equal to the ones that are already on it. And if you start getting about 4 feet, you should probably add about 2 extra sets. Like Castle Creations and Contronic and some other companies make these little circuit boards that have like 3 or 4 or 6 capacitors on them, and you solder it right across. And that is to keep the DC voltage more stable at the input of the speed controller and minimize that loss down the lines due to the phases switching. So it does help. What it does is if you have that current fluctuating a lot, what you're doing is current is rushing in and out and in and out and in and out of those capacitors 8,000 times. And what will happen is it's like bending a paperclip back and forth, and eventually it will heat up the capacitors and cause them to fail. And when the capacitors fail, then the speed controllers fail because you lose that filtering. So it's important that you add a couple extra capacitors on there for long leads.
But as far as the length of the leads, the rule of thumb will be about 16 inches then? If you exceed 12 inches? Or?
Yeah, if you get longer than maybe 16, 18 inches, you should be concerned about it. Start adding some bigger capacitors.
Well, the small things like this.
No, stuff like this is not a problem. You're just not pulling enough current to be an issue.
What about adding caps on the positive negative speed controller for all voltage applications? Is that necessary or?
Not anymore. And it used to do that with brushed motors to calm the noise and the sparks from the brushes, but these are brushless motors, so that's not even a concern.
Okay, so this idea that the capacitors can be damaged over time in the speed controller.
Well, we're talking different capacitors now. The capacitors, like on brushed motors, were actually soldered on the brush from the brushes of the motor to the can. The capacitors on the input of the speed controller,
That's what I'm talking about.
those can be damaged by using too long of motor leads and running the speed controller at very high current ratings. Because every time the transistors fire and you get a pulse going to the motor, you're actually using that capacitor as a reservoir to feed that extra power to the motor while the battery's trying to push it down the wires. And so the voltage, if you actually look at it at the capacitors, it might be 12 volts, but it's actually going like this between 11 and 12 every time it fires. And so basically you're pushing her in and out and in and out and in and out. And it's analogous to taking a paper clip and bending it back and forth and back and forth, because that current rushing in and out and in and out heats up the plates in the capacitor. And over time they'll get so hot that they'll boil off the electrolyte that's inside of them, and then the cap will pop open from the pressure, and then it'll short out, and then get damaged.
Could you say a few words about the effect of the sensorless or censored motors?
Well, all of the
on
brushless
efficiency?
motors that you see over here are sensorless design. They rely on that pulse, on that unused phase during each firing cycle to get the sense when the motor's at a certain position. Censored motors actually have 3 magnetic sensors, they're called Hall effect sensors, inside the motor itself. And as the magnets in the motor go past these 3 sensors look at 4 different magnets at the same time because they're spaced, so one's here, one's halfway between 2, and the other one's halfway between the other 2. So they can sense, and they can also sense North Pole versus South Pole on the magnets. So when you turn on the motor, the speed controller knows exactly where the motor is in its phase cycle, and it knows which way to turn it because it's looking at 3 sensors at the same time. And so you can start a censored motor into a heavy load like a car or something, and it will take right off and run. Where a sensorless motor, if you've ever opened up the throttle on them, sometimes they go, and then they'll take off running. During that first little bit, they're trying to figure out which way is which, and then it wiggles enough to where it sends a couple pulses to the speed control and go, oh, okay, I know where you're at now, then it can start spinning it. A censored motor will just take off running in the proper direction every time because it already knows where the motor is with respect to the magnets.
So either technology doesn't have much of an effect on the efficiency of the motor?
It
This
has
one is
no effect on the
smoothness.
power output or efficiency of the motor. It's only good for starting the motor up accurately and in the right direction every single time.
Hence the application of the cars.
Right, because when you're